All right, let's talk about isosceles and equilateral triangles. So there's a lot of ways to think about this, but really the big picture here is just these simple two biconditionals. And it's if I encounter any triangle where two sides are congruent, then that means that the angles opposite those sides must also be congruent. So if I have two congruent sides, then I have two congruent angles, and we know which two. They're the two opposite the two sides. And then similarly, the reverse is true, the converse is true. So if I encounter any triangle where two angles are the same, then I know that the sides opposite those angles, like if the angle was a flashlight and it's shining at a wall, right? This flashlight is shining at this wall. So whichever one it opens up to or it's across from, those two sides must be congruent. And then if we just use that twice, and I'll show you how to use it twice below, that must mean, right, if these two are congruent, then these two are. And if these two are congruent, then these two angles are the same. And so then all the angles have to be the same by transitive. And so as a consequence of that first biconditional, that just means as we use it twice, that three sides congruent then means all three angles are congruent. So equilateral triangle means equiangular triangle, and then the converse is true too. So if we come across an equiangular triangle where all three angles are the same, that means the reverse order, that means that triangle must be equilateral. So equiangular implies, I don't think that's equiangular. Oh, spelling is so difficult. Okay, let's go down. All right. Oh, and by the way, just a little side note I wrote in green here. If all three angles are the same and they add up to 180, right? X plus X. So if all three are the same and add to 180, that's just 3x is 180. You divide 180, and every single time those equilateral triangles, those equiangular triangles, have 60-degree angles every single time. That's super useful and will come up a ton, not only as we're dealing with problems with this section, but as we're dealing with shapes in the future, especially regular polygons, trigonometry. So these 60-degree angles come up a lot. Okay. So just refresh on isosceles triangle vocab. We did this in the past, but in terms of the sides, the base doesn't have to be on bottom, but the two congruent sides are called legs, no matter which way I rotate it. The two congruent ones, legs, and then the non-congruent, the only one that's not congruent is called the base, okay? And then the angle between the two congruent sides is called the vertex, and then the other two angles along the base are called the base angles, okay? So our first theorem is going to be called the base angle theorem, saying that if we have two congruent sides, then the base angles are congruent. So that's the name of our first theorem. And again, we'll prove it down below. We'll talk about it a lot. So two biconditionals. The base angle theorem says if two sides of a triangle are the same, then, and here's the base angle theorem saying then, we know the angles opposite those must be congruent. Okay, so that's the original base angle theorem. We'll prove it below. And then the converse going in reverse says if we encounter a triangle with two angles are congruent, then again, these pink lines kind of show you which sides must be congruent. So then we know these two sides are congruent. That's the converse. I'm totally okay with you just calling this the base angle biconditional, and then you could interchangeably use it to go either direction. That's the goal here. So we're going to prove it both directions, and then it's just this easy give and take. If you find sides, you know angles. If you find angles, you know sides, and it's one super useful theorem, okay? And then a corollary here is just what we mentioned above. So I'm not going to repeat myself, but three sides, three angles, or three angles means three sides. And we call that or our book calls that the corollary to the base angle theorem and the converse of the corollary of the base angle theorem. I think just like equilateral triangle biconditional, that'd be a really clear name. Biconditional, having to do with equilateral triangles. Or you could say like equilateral triangle if and only if. Equiangular. So you could like write that. That would be super clear to me on a test or quiz, showing I know exactly what you're talking about. You know what you're talking about. All right, so let's apply it algebraically once or twice. And then I'll give you a couple alternative perspectives on how to look at it. And then we'll go ahead and prove the theorem. Because I want to save the proof a little bit. Not that it's anything special, but sometimes people can lose attention span when we go into the proof. Okay, so here we go. Algebraically, let's look at this triangle. It says all three angles are the same. it says all three sides are the same. So the implication then is anytime we find a triangle with three congruent sides, that means all three angles are the same. And as we mentioned above, if all three angles are the same, that means that all three angles, 180 divided by three equal angles, are 60 degrees. So right away in this problem, we go 3x must be 60 degrees. And so dividing by 3, we know x is 20 degrees. Oh, classic. I love it. Okay, over here, number 2, we're going to use the converse of the base angle theorem, because here we're given two angles in a triangle are congruent. That means that the sides opposite those must be congruent. So we now know by the converse of the base angle theorem that these are the same. So we know 5x plus 5 equals 35. So subtracting 5, dividing by 5, x is 6. Great, okay? 13, we're going to use the forwards of the base angle theorem, the original theorem, which is saying if I encounter a triangle where any two sides are the same, I know that the angles opposite those sides must be the same. So 9x equals 72. We divide by 9, we get x equals 8. Great, boom. Used almost all four of our both direction, corollaries, and base angles, okay? All right, so let's go ahead and think about it another way, right? Because again, looking at things in multiple perspectives helps you see it in different lights. If you just looked at a cube dead on, you'd never even understand that it was a three-dimensional object. You'd see a square and go, I understand, I'm confident, I know. But actually, the more time you take to just spin it around and look at it, maybe on the point and turn it, and now it's like a diamond shape. It's got maybe other colors behind. So, I mean, just take a second. So another way to think about it is, how many lines of symmetry does a triangle have? And that's it, right? Because it's actually more powerful than the theorem above. We're just not going to prove every facet yet, but they'll all come up here. They're growing, they're percolating. So here's the thing, right? So what if I do, okay, so scaling, there's no line of symmetry, right? None of these are the same, so there's no like mirror imaging here. But an isosceles triangle has exactly one line of symmetry, or by this book's definition where it's at least two sides congruent, so an equilateral triangle is a special case, then we would technically say it's one or more because equilateral is isosceles. But anyways, an isosceles triangle has one line of symmetry. What this means, I mean, think about this. That means everything on the left is a mirror image of the right. So that means this side is congruent to this side. This angle is congruent to this angle. That was our theorem so far. But beyond that, what does it mean? It actually means this is the midpoint to the bottom, right? Mirror image sides. It also means these two angles down here are the same. And what two angles are the same and add up to 180? Well, those are 90. So it actually means this is perpendicular down here. And this actually means this up here must be the angle bisector because it's just mirror image, right? So that's the big idea here, is this line down the middle of an isosceles triangle, we're going to use it all the time. It is not only the angle bisector, and this whole next chapter we're going to investigate this, but it's the angle bisector, which also passes through the midpoint of the bottom and is perpendicular. So it's the altitude, it's the median, it's the angle bisector, and it's the perpendicular bisector. It's every single thing. It perfectly splits this triangle down the middle. So if you just remember that an isosceles triangle is one line of symmetry and everything on the left is the same as everything on the right, you can solve for all the x's and the y's and whatever problem you want, because you just look at this and go, I know everything over here matches its counterpart, right? If I go up here to this last problem, I go, oh, look at this. I encountered enough to know it's an isosceles triangle here and here. So, pa-chow! Well, I missed pretty bad there. Let's pa-chow again. Pa-chow! And now I know everything. So this matches here, this angle matches here, this angle matches here. 16 is split into 8 and 8. So that's the idea, and it lets you solve for whatever you want. Same thing on the next problem. You go, oh, look, I encountered enough information to know it's isosceles, so ka-chow! I know everything from this side is the same as that side. Right? That's a cool way to look at it. Equilateral, same thing, except now it's got 3 lines of symmetry. So you cut it this way, it's isosceles. You cut it this way, it's isosceles. Woof, I missed pretty bad. And then you cut it this way, and it's isosceles. Yeah, I'm missing. There we go. Oh, that looks pretty good. Okay, so 3 lines of symmetry, meaning anything on this side is the same as anything on this side, but 3 different ways. And I mean, just that rotational symmetry of so many multiple lines. I mean, that's really cool to just think about. We'll get to rotational symmetry later on. Okay, but then what if there's even another perspective here? Okay, so another perspective is in one triangle, and we're going to get to this in multiple different ways too. So in one triangle, we actually have this relationship, and again, this is, I'm like foreshadowing the future, but we actually have that the biggest angle is opposite the biggest side. You could think of it like they're proportional, like the bigger an angle gets, the bigger the side gets, and the smaller the smaller. The relationship isn't linear, so it's not literally a proportion like it's 3/4 times, but there's even a, I mean, the law of sines is literally this thing. And so there's a numerical way you can transition from angle to side, but we'll get there, we'll get there. Whew, you guys are getting excited, antsy for the future. So the medium angle is across from the medium side. The smallest is across from the smallest side. And then what that means is if we ever encounter a triangle over like on the right, you go, oh yeah, biggest is across from biggest. And then these other two angles are equal, so they're across from, right? The proportionality that I'm discussing would mean that these sides are equivalent, right? That's another way to even look at it. And we'll establish this relationship in the future, the greater than, less than inequality. But then we'll even take it further and when we get to trig, we'll get a numerical calculation where you can use the angles to determine the sides they open up to in a triangle. So even another way to see this. So many different ways to look at it. So let's go ahead and prove the base angle theorem. Then we'll prove the converse, and we'll do a bunch of homework problems, okay? So how can we prove this, okay? Well, how did I say in the last video, we're going to prove pretty much everything. If they say prove these angles are the same, right? 90% of the time, especially in this chapter, but moving forward too, the way we do that is with congruent triangles. And you say, well, how the heck do I have congruent triangles here? This is crazy town. Okay, so there's actually a really elegant way to do this without even making a new triangle. You could actually say, well, I mean, this is cool. This might be confusing for some people, so I'll maybe do two separate proofs. Let's do one on the left here. Oh, I meant to switch to blue here. It's less burning the retinas. Okay, so in this triangle, though, I could say, well, I know AB is congruent to BC, and that was given. And then I could also say, well, I know BC is congruent to AB. And you'd be like, what are you doing, Mr. Lure? You are freaking crazy. And then over here, I'd be like, well, I also know, and I'm going to erase this for a second. I'll shrink it later. I also know AC is congruent to AC. And you're like, what are you doing? Well, with these three combined, what I just proved is I said, okay, so this side is the same as this side, and this side is the same as itself. So look at what I know now. Triangle ABC is actually congruent to, wait for it here. Triangle ABC to A to B to C, so across 1 dash, 1 dash, and then 2 to finish off. So ABC is actually congruent to triangle C to B to A. Think about it. I just went over the same congruent sides, the same angle. So this is congruent to triangle CBA. Like, what the heck just happened? The same triangle, but it's not the same triangle. Order matters. And so these were all, what was this? This was given. This was given. This is reflexive prop of congruence. And then this would be side, 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 triangle congruence. And then you say, oh, well, what are you doing with this crazy mirror image inside of itself, like Inception thing? Well, look at this. Angle first letter is congruent to angle first letter. So I know angle A is congruent to angle C by CPCTC. So that's a really clever, like, elegant little thing. Now, you don't need to see that. That's crazy town. So in general, there's a more like direct approach. I'll kind of shrink this off to the side. Okay, we're going to do the more direct approach. The more direct approach, when you see an isosceles triangle, just in general, the rule of thumb is slice that sucker in half. Just feel the temptation, feel the enjoyment in slicing that thing in half, right? Like you're playing Fruit Ninja, or you've got like a warm sword and all these like butter like dummies, and you just get to slice through them. I mean, that would be enjoyable. So let's just do that. So we're going to slice this in half. Now remember, when you add an auxiliary line to a picture, you can't make multiple assumptions. So you can't say, I'm going to make the angle bisector, which also like passes through point A and then like draws a smiley face. Like you can't make all these additional assumptions. What that creates is an impossible scenario. So instead, you make one assumption because you know certain things exist. So for example, I could say, well, I know there's a midpoint to AC. Okay, and I know between any 2 points, so the midpoint would be these are congruent, right? And I know I could then just connect those between any 2 points. There is a line. Now, if this was a super rigorous, like geometry honors course, I would have to establish that like a midpoint exists. And we would talk about what existence is, and then we'd say between any 2 points there is a line, so I can connect, I don't know, let's call it M. I can connect B to M. That exists because of the postulate that says between 2 points there is a line. But instead, you know what? I'm just going to go ahead and I'm going to say draw B to M, where M is midpoint of AC. And I'm going to say you don't even need to give a reason for that, but that's just like an underlying start to a proof. Okay, well, now that you did that, you can say, oh, well, then I know, and this is just adding an auxiliary line. There's no like fancy words you need to put here, but add an auxiliary line with like one assumption is kind of the big idea here. Is one thing, it's not even an assumption, but essentially one superpower, one ability. It is the angle bisector, is the midpoint. It's not two things. It's not the midpoint and perpendicular kind of thing. All right. So anyways, so we drew that. Well, then we know that AM is congruent to MC. Okay. And that's because that's the very definition of a midpoint. Okay. Well, what can we do with these two triangles now? We know those are congruent. And how do we get this triangle's congruent to this one? Oh, gosh darn it. Well, look at this. Look at this. We were given these are the same. So now we got two sides. So we could either go for side angle side, but that's what we're trying to prove. So we can't probably get that in between. That's going to be our end goal. So instead, we could say this side reflects the property is congruent to itself. So let's go ahead and say AB is congruent to BC, okay? And that was a given. And then we could also say BM is equal or is congruent to BM, and that's the reflexive property. So BM congruent to BM, okay? And that's reflexive property of congruence. And then with those three combined, again, we use SSS there. And so now it's just the exact same as the left kind of. I mean, not the same triangles, but same reasoning here. So now we get these two congruent triangles by SSS, triangle congruence. And then from there, we're going to say, well, then we know the angles, angle A and angle C, if we lined up the triangles right, should be congruent by CPCTC. So now let's just check the order up here. So if we go across 1 marking, 2 marking, 3 marking, and 1, 2, 3, then we have the order is BAM, bam, is congruent to, and let's check on the right, so BAN, and then B to C to M, so B to C to M. So triangle BCM. And then we just check, okay? So is A congruent to C? Yeah, A is the second letter, C is the second letter. So angle A in that triangle is the same as angle C, CBCTC. So then we just do essentially the same thing down here. I'm not going to do necessarily the short, elegant proof, but you could do the same thing here. You could say, well, if these angles are the same and this is the same as itself, well, then ASA is the same as, and then you just do ASA in the other direction, ASA, and you could say triangle ABC and triangle CBA are the same, and so they're corresponding. So we could do the elegant proof again, but let's do it a more common, like the way the book does it. So what we're going to do here is we start with that. We want to get the sides are congruent. Again, 90% of the time, if not more, the way we do that is with congruent triangles. This is the superpower of the class, is like to find triangles and solve them and use them and everything. I mean, even when you get into like computer generated graphics and video games, everything is drawn in terms of triangles. Everything, because we can know everything about triangles and use it and make it efficient. Anyways, I digress. Okay, let's go back to here. Okay, so what we're going to do is cut this thing in half, okay? Now, how we cut it in half is up to us, okay? For example, if I were to use the midpoint again here, then I'd say these two are the same and this is equal to itself. But look at those two triangles, though. What a congruence shortcut would that be? That would be two sides and an angle not between them. That would be ASS. So we don't want to connect to the midpoint here. What's something else we could do? Well, I know we could just bisect to this angle. No assumption. Who knows where it hits here? I mean, we'll give it a name. We'll label it M. But really, this is just an angle bisector. We know nothing about right angle down here. We know nothing about whether it hits the midpoint. We don't care. We can't make more assumptions. We could prove that stuff, but we're not going to. All we're going to say is draw the angle bisector. So draw angle bisector of angle ABC. Okay, so that's what we do first. We're adding an auxiliary line. So we're just adding an auxiliary line that exists, okay? Auxiliary line that exists. Okay, that's the key, is that it's a possibility. And we all agree it's a possibility. There's certain rules, but again, we're not going to get into those details in this course. Okay, so now that we've got that, we could say, oh, well, by the very definition of an angle bisector, right? We could just use that word. We could say, well, then we know angle ABM is congruent to angle MBC. And again, you'd be like, well, Mr. You could just make up anything and say anything's congruent because it's the angle bisector. But again, the key is you only make one assumption. I am saying this is the angle bisector. I know every angle can be cut in half. Every single angle. Come up with any number. 40 degrees. Boom, cut it in half. There's 20 degrees. There's only one angle bisector in the middle of that cuts it exactly in half. That exists, right? I don't assume that it does other things as well. And so, yes, you can make the midpoint. You can draw the perpendicular, but you don't necessarily know what other implications it will have. So that was it. I drew that line. That's what I know. I also know that angle A is congruent to angle C, right? Because that was given. Now, what else could we get here? Let's look at the picture. Oh, and I should have done two angle marks there, so it's not the same as A and C. Well, we have that reflexive property here. So BM, again, is congruent to BM. And so do we have enough information here then? That was a reflexive property. Do we have enough information then to say that the triangles are congruent? Well, see, that's AAS. Oh, yeah, AAS is a triangle congruent shortcut that does work. So this would tell us that triangle ABM, and just following the angle, so angle 1 to 2 to nothing, so is CBM. So ABM and CBM are the same. Okay, and then let's look at, triangle CBM are the same. That was by AAS, triangle congruence. Okay, let's look up here and see. We were trying to say AB was the same as CB. So AB is the same as CB. Oh, yeah, well, those are corresponding parts. So corresponding parts of congruent triangles are congruent. Oh my God, that was a tongue twister while I was trying to write the previous step at the same time. Woo, that was good. Okay, so there we just proved the two theorems, all right? So the corollary there, so that was remember, that was the converse, and this was the original, but it's just back and forth. You can go either direction. It's a biconditional now. We've given you that superpower. So all the corollary means, right, is it's just a little eddy current, right? If here's the big theorem, then here's just, boop, a little like wart on the side. Just one extra step to the left, one extra step to the right. Look at what we could do with this. So all we do is say, hey, look at this equilateral triangle. Well, I know that these two sides are the same. So now I have that the opposite angles, these two are the same. And I go, but hey. I'm looking at this for a different perspective. Mr. Dilloughery said have an open mind. So I'm going to look at it a different way. So, right? So I'm saying these two are congruent. So then I know that these angles are congruent. Right? I just used the base angle theorem twice. But wait a second. Transitive property says if this angle is the same as this one and this one's the same as this one, they're both the same as this bottom left angle. So then transitive means the A and C must be the same as one another. So now we have all three are the same. So all we did was use the base angle theorem twice. Done. We proved it. Right? Same thing here. We just go, oh, if we're talking about these two angles, well then these two sides are the same. And if we're talking about these two angles, then these two sides are the same. put those together, and that means all of the sides are the same. So you just use the converse of the base angle twice. That's why it's a corollary, right? It's literally a two-step proof. One step is use the base angle theorem. The next step is base angle theorem. Oh, I guess you could even put those together in one step with two things written with one reason, base angle theorem. And then the last step would be transitive property. Done. Okay. So now let's jump into some homework problems here. Explain how many angles in an isosceles triangle must be given to find the measures of the other angles. So this is how you'll use this really often, like algebraically. So if I have an isosceles triangle and I'm given this is 50 degrees, or if I'm given an isosceles triangle and I'm given one of the base angles is, I don't know, like 20 degrees, I can solve for every single angle in here, okay? Let's do it. So in the right one, it's a little easier. We go, well, these two sides are congruent, so the angles opposite them are congruent. So just to erase that mess, we now have this is 20 degrees. Well, the triangle adds up to 180, so this top angle is just 180 minus 20 minus 20, and so it's just 140 degrees. So using just one base angle, we could solve for any other angle. Well, what if we didn't have a base angle? What if we had the vertex angle instead? Again, the vertex is between the two congruent sides, and so we say, well, we used up 50 of those 180 degrees. We have 130 left. But we know that these two must be the same, so we split that 130 equally. And so both of these must be 65 and 65. And so if you just have the vertex angle, you could solve for the others. If you're more comfortable with like formulaic algebra, you could just say, well, let this angle be x. And if the sides are congruent, you know this is x too. So then you just go, whoops, not 150, just 50. Plus x equals 180, and then you solve with algebra. But the idea is you only need a single angle now in an isosceles triangle. What about an equilateral triangle? Trick question. How many angles do you need to know in the equilateral triangle to solve for all the angles? None. You know them all. What are the angles in an equilateral triangle? I was paused for effect. It's always 60. So you don't need to be given any angles. You know they're 60 always. Anytime you find three congruent sides in a triangle, you always know their angles are 60. So for an equilateral, you need nothing. You know them all. For an isosceles triangle, you just need a single angle and you can solve for the rest. Okay, so write a two-column proof. You know that it's isosceles, and notice they clearly said with vertex angle C. Thank you, book, for not making some assumption about where the base is. I like that clear communication. Okay, so we know that that's the vertex angle. So if it's isosceles, we'll use, and I'm going to write it out. So we'll say CTE is isosceles, and then I'll even add the with vertex angle C. Now, how could we use this? Right? Hopefully it's starting to click. Notice I see an English language word. And so how do we use a word? We always use that by definition. And so we say, what is the definition? Now, this is where people get a little loosey-goosey, okay? The definition of an isosceles triangle, the way we defined it, was two congruent sides. Then to get to the angles, we use the base angle theorem. To use the definition of isosceles and say the angles are congruent, that's a little too hand-wavy for me. Some teachers might be okay. Some books might define isosceles with two angles congruent. And because that's biconditional, equivalent to two congruent sides, that's okay. Your book could do that. So in our book, it does congruent sides. So we can only say that if this is the vertex, that means these are the two legs. So we could say CT is congruent to angle CE, or to side CE, sorry. Okay, and that was by the very definition of isosceles. Whoa, isosceles. Okay, so now what could we do? Gosh, well, how could we use that, huh? Well, look it up here. This is the key, right? We have this angle given to us. So let's state that, okay? Let's say measure of angle T is 60 degrees. I don't like that this book leaves out this degrees. I don't like that. Okay, and then so this was given. Okay, well, how could we use that, huh? Oh, well, look at this. If we know the sides are the same, well, we know the angles are the same. So angle T is the same as angle E. Okay, well, that's useful. We're not in the world of algebra yet, right? So this would be the base angle. I'll call it the base angle biconditional, but you could call it the base angle theorem and then separate it from the converse if you want. Okay, so we know the angles are the same. Well, let's use that. So I'm going to say now that that measure of angle T is equal to measure of angle E. That's the very definition of congruent segments, Okay? And so now I could bring this down. I could say, well, if I know the angles are, oh, and I'm going to have to just add an extra page here. I like getting really detailed with my proofs, okay? So I know these are equal, so I can substitute them, and I can say, well, then that means the measure of angle E is 60 degrees, okay? Okay, and that was either transitive, I'm going to say transitive property of equality, because if they're both equal to the measure of angle T, so that's transitive property of equality, you could have said substitution, totally valid. Now, how could we use that? Okay, so we have that this is 60 and this is 60. What does that mean, like, in terms of our triangle, right? So if we go, this is, I'm just looking down there, if we go, this is 60, then what could we do? Oh, wait a second, I see where you're going with this, right? If those two are 60, then couldn't we solve for angle C? Well, let's solve for angle C. So how could we solve for angle C? Well, the way we could do that is we could bring in the fact that measure of angle C plus measure of angle T plus measure of angle E equals 180 degrees. And how do you know that it adds up to 180? We don't jump to, like, the measure of one angle is 180 minus stuff. That's the triangle sum theorem plus algebra. We're just going to state the theorem. We're going to be really clear here. So this is the triangle sum theorem. Okay, we prove that again. We prove that with parallel lines, and then we said, oh, this angle alternate interior, this angle alternate interior. Remember, so it was a cool little, like, why. You're like, oh, I've always used that and I never knew why. Okay, so anyways, we got that. Well, now we can substitute this and this in, and we get measure of angle C plus 60 degrees plus 60 degrees equals 180 degrees. And this is where now you could say this was substitution. Sorry, before we get ahead of ourselves. Now we could start doing, well, what if you had like 3 steps of algebra, 4 steps of algebra? I am going to be okay. This is still really 1 step of algebra, but I'd be okay with you then saying the measure of angle C equals 120 degrees when it's clear all you're doing is solving an algebraic equation. I'm okay with you just saying algebra. That's the way IXL would do it too. So they just say, those steps are just the properties of equality, okay? We practiced them in a previous course, we've used them. Or you could have called this the subtraction property of equality, because really all we did was subtract 120 from both sides. Easy, either way. Oh my gosh, and I wrote 120. Yes, I can do subtraction. I was saying subtract 120, so it's 60 degrees. Okay, well, if this is 60 and the other is 60 and the other is 60, well then I could, and this is going to be, how could I connect these? This isn't going to be pretty. I don't see a way where I could get something, I could get an arrow from T all the way down. Well, that's going to be a little sloppy, but the idea is simply that now I know, oh, how am I going to connect these? Okay, well, I'll do it in a different color. So I know that this and this and this mean that, and I could list them in some way. I'm just going to write them out. Measure of angle C equals measure of angle T equals measure of angle E. Yes. And that we could just call that substitution. You could call that algebra, but we have all of these are equal. And so now what that means is our corollary then says, what are the sides? Oh, it's CTE. There's only 3 sides. So that means CT is congruent to CE is congruent to TE. And that's the, you could call that, I'm going to call that the equiangular if and only if, or the biconditional equilateral. I like that one. That's just so clear, right? Again, it's only for triangles, so I'll put a little triangle symbol in there. And then if all 3 sides are congruent, then triangle CTE is equilateral. And that is by the very definition, all 3 sides are the same. So that's by the very definition of equilateral triangle. Okay, so I went maybe more detailed than the book did there, but that was a fun one, right? So we just are using those exact corollaries. Okay, well, what about, whoa, going crazy here. What about this one? Okay, this is a really common one where you get 2 isosceles triangles side by side. There's like 10 of these in this book. Okay, so let's go. PQ is congruent to QS. And then we also have QR is the same as RS. And then they give us a single angle. So PRS, so this one over on the bottom left is 72 degrees. And then it says what's the measure of some other angle. But we can solve for every angle in this entire picture, okay? Here's the idea. in the left triangle here, we go, okay, so we've got this isosceles triangle. This is that scenario where these two angles are the same because of the base angle theorem in that triangle. And so we can go 180 minus the 72 that's used up, divided by the 2 that are left, or you go x plus 72 equals 180, and you solve for x. So I'm going to do it on the left. Let's say we got 108 divided by 2, so we got 54 degrees. So I'm going to erase this work. So we got a 54 here and a 54 here. So we're done with that left triangle. What could we do with the right triangle? We don't have any avenue over. Look at this. We don't have that. We don't have this 2 angles to give us the third angle of the big triangle. But oh, wait a second. Linear pair. Okay, so this is just 180 minus 54, so that's 126. That's good. But now where could we go? Oh, wait a second. Now we're in the exact scenario we were in the first time, except now here's the triangle, and now here's our x and our x. So again, we could either say, well, of the 180, we used up 126, and then we just divide that in half to see what each of the 2 equal angles are. Or you could say x plus 126 equals 180 and solve for it algebraically. It's the same steps. So here we go. It's 54 divided by 2. Oh, let's even do it another way. Okay, what if we instead said, wait a second, this is a vertical angle. So here's A and B, and then the, not vertical, I meant external angle, this. So that means A and B, and I don't even need an A and a B because they're the same A and A, and the external angle theorem says A plus A equals 54 degrees. So then 2A is 54, and we get A is 27. Now that's not something you need to recall. We don't use the external angle theorem that often, but that's something you could use there. Or you could have done it in a straightforward sense. So this is 27 degrees, this is 27 degrees, and it just asks for one of the angles. So it asks for this one. Okay, cool problem. So let's look at this picture. And this is saying like use these theorems over and over, but in like, you know, a complex diagram where there's lots of intersections. So really be clear about what isosceles triangles you have. So if LT is the same as LR, what angles are the same? That's this angle and this angle. So it's angle LTR and angle LRT. Okay, that was a good one. Let's see the next one. The next one says LX and LW. So LX, oh, so same thing here, but just longer. And then this one. So if those two are the same, well, then those base angles here and here are the same. And there's no ambiguity, so I could just call that angle X and angle W. Those are like the only ones without ambiguity in the whole picture. Whew, saved us there for a second. Okay, and then what about SL and QL? So SL and QL, that's this side from here up. And from here up, so in that isosceles triangle, these are the base angles. So that would be angle LSQ and angle QS. Dang it, I tried to do it without looking at the picture. I should always take the time. It's a lesson, right? Just take the time and do it right. Otherwise, you got to redo it, okay? So from L to Q to S. All right, so let's look at the angles now, okay? What about LXY? So L to XY, so this angle is the same as LYX, so this angle. If those are the base angles, that means this entire side and this entire side are the 2 congruent sides. So that means we've got LX and LY. So LX, LY. So the reason I'm writing it like this, it just said name the 2. If it said write the congruent statement, you just put a congruence in between with a comma. Neither one is right or wrong. It just said name, so I'm putting a comma like it's a list, but it doesn't. If you put this is congruent to that, that's extra same correct. Okay, so LSR, that's this angle, is the same as LRS, that's this angle. Oh, so that's just this side and this side. So LS and LR. And last one here in this set, LYW. Okay, so LYW, that's this angle, is the same as LWY. So this angle, that's this side, LY, with this side, LW. So LY, LW. So really good at just practicing using that. Okay, so now it's saying, whoa, we got these isosceles triangles and we got this one angle. So it's kind of like what we did up here, except now there's 3 triangles here. Woo-wee. Okay, and JKN. Now, see, it hid something up here. Now, we can see this is isosceles, and we can see this is isosceles. So that's given. However, JKN. So it tells us that this is 130, but we don't know how much of it is in each triangle. So we can't use it yet, but I think we'll be able to. Okay, so let's just solve for everything here. Well, if this on the right is 20, base angle theorem says this is 20, and then that means this angle here is the rest, so 180 minus 20 and 20 is 140 degrees. And then in the middle triangle, this is 18 degrees. Okay, and so then we're going to do that, well, the rest, like, because I'm going to erase the 130, but we remember it's there, okay? So in that triangle, we know that these two angles, or the base angles, are congruent because of these two congruent sides. So then we do that 180 minus, how many degrees? 18 degrees. And then we divide the leftovers evenly between these two angles. So then we just say divided by 2. Or you could say x plus 18 is 180, and algebra that thing. Okay, so this is 162 divided by 2. That's 81 degrees. And so I'm going to go ahead and erase these. And I'm going to put an 81 degrees here and an 81 degrees. Now, if you didn't read the given, you'd be stumped. You'd be like, well, what can I do in this other triangle? I got 25. It's not isosceles. I don't have another angle, but you do. JKN is 130. So if this whole angle is 130, you go 130 minus 81. That's almost 50. That's 49 degrees left over. So that means this is 49 degrees. And if that's 49 and we have a 25 down here, well, then angle J is just 180 minus the 49 and minus the 25. So that's 180 minus, what, 60, 74. So that's 106. And so we got a 106 degrees there. And then we just answer all the questions they're asking for angles. But we found every single angle. So whatever it's asking for, we can answer. Okay. Let's go back here. Oh, this is just that same problem we did again. So there's two isosceles triangles. It says we get in a 28. And DG is the same as FG is. Okay, perfect. So let's do it. So this is the same one as before, except instead of starting with the vertex angle and going to base angles, we're doing the opposite of that. We're starting with a base angle and we're going the other direction. So if that's 28, that means base angle 28. Then we add that up, we go, oof, 180 minus a 28 and a 28. What's that? That's 180 minus a 56. So that's 130, that's 124. Okay, and then we go same linear pair gets us into that other triangle. That's our like secret key code to get over there. So this is our 56 right here. Again, we could use the external angle theorem to say these two angles add up to the external angle. It would save you a second, maybe, but we didn't do that. Okay, and then in this other triangle, because of these two sides here, whoa, don't get crazy on me now, Apple Pencil. Because of those two sides here, well, then this is 56 also. And then we go, oh, we just, up top, we go 180 minus a 56 and a 56. That's 180 minus 112. And then that's 68 degrees. And so here's the 68 degrees. And one thing you could always double check at the end of a problem, just to be like, did I make a mistake? Is because you worked with all these separate things, but it makes one big triangle, you could always say, do these three angles add up to 180? So I'm just going to do that really quick. So is a 28 plus the second angle, 28 plus 68, plus the third angle, 56. Does that add up to 180? Okay. So this is, I'm going to add these two together. So we get a 56. Plus, I'm going to add these two together. We get 110, 114. Yeah? Is that 114, 110? No, 124, sorry. And then we add those together and we get 180. Check. Okay, so that's just an easy at the end go, whew, like something worked out, right? It probably didn't make a mistake there. All right, so that's helpful. Let's go on. I think I'm only doing like maybe two more or so. Oh, three more because I added that round one there. Okay, so we're given that this triangle is equilateral and that xj bisects angle x. So we have that that's what the bisects means, is those angles are the same. We want to show that J is the midpoint of KF. Well, to show it's the midpoint, what's the definition of midpoint, right? So if we down here at the bottom go, J is midpoint of KF. If we're ending there, what's the second to last step? What's the penultimate? What a cool word, penultimate, right? The ultimate being the last, penultimate being the second to last. If that's the last step, how would we get to it is the midpoint? How would we get to an English language word? Well, the only way we would get there is by the definition of a midpoint. So what would we have right before that? Well, the definition of a midpoint says if, or I mean it's an if and only if it goes both directions, if the two segments are congruent. So really it's saying show KJ is congruent to JF. That's what it's saying one step further. Okay, well, how could we show that's congruent? Well, in general, again, if we want to show two segments are congruent, especially when it's showing us a picture of two triangles, well, the way we're going to do it is with triangles being congruent. Now, yes, I understand there's actually three triangles, big and left and right. Okay, let's not mince words here. So we want to show that the left and right triangles are the same. If we can, CPCTC will get us this last step. So before this, we need to get the two triangles are the same. And I'm not going to guess at the order of the triangles because sometimes it surprises you. So let's start at the top, okay? So if we want to do this, and maybe I'll slide this over to the side. It looks like we have more room over here. Okay, so let's start here. Let's say, well, we were given that triangle X, well, that's not an X, triangle XKF is equilateral. How could we use that? Well, that would tell us that all the sides are congruent. Well, what sides do we need to use? If we're trying to get that the triangle on the left is congruent to the triangle on the right, this side being congruent to this doesn't help. And this side being congruent to this doesn't help because I want to know just a piece of this left triangle. One of the three sides or one of the three angles is the same as one of the three sides or one of the three angles over here. So the only one that's useful is this. So we're going to say, well, that tells us, oh, that was given. Well, that tells us that side KX must be congruent to side FX. Okay? That was by the very definition of that word. So definition of equilateral triangle. Okay, so now what else do we have about the two? Okay, well, let's see what else. Oh, I'm just erasing the wrong things here. What else do we know? Oh, well, look, in this left triangle and right triangle, classic, they share a side. So we know this side XJ is the same on the left triangle as it is in the right triangle because it's the same as itself. So let's just right here, just say XJ is congruent to itself because we always need three facts to know these triangles are congruent. That's the reflexive property of congruence. Okay, and then let's look at this other one. What's the third piece? Well, remember the other given. The other given is that X, well, that's a crazy X, XJ bisects angle X, right? So that was given. And what that tells us is, by the very definition of an angle bisector, that tells us that angle KXJ is congruent to angle, that's KXJ, FXJ. And that's by the definition of an angle bisector. Okay, well, now we've got our three sides. We got this side, we got this side. I'm going to move those down a little bit. So let's delete that and let's move these down a little so they're on the level. Okay, so these three combined give us, and I'm just going to show some markings so I can get, so this is congruent to itself, these are congruent to each other, and this is congruent to this. So what that tells me is 1 to 2 and 1 to 2, the order of these triangles is triangle JXK. Remember, I could pick any order for the first triangle, but the second order then is locked in. So JXF, and that was by, I'm going to erase this right here. That was by side angle side. I have two sides and the angle between them. So that's side angle side, which is a congruent shortcut that works. So SAS triangle congruence. Great. And then does the order match? K to J is 3 to 1. F to J 3 to 1. Or I mean JF is the same. Woo! We did it, you guys. That was good. Okay, so two more problems. Let's see. MLP is isosceles. Okay, that's good. We're going to use that. So it shows us in the picture these are congruent. We don't actually know that. The reason it's doing that is so it doesn't have to say, and the vertex is. It's saving itself from writing those words by showing you which ones are the legs. However, we would have to state definition of isosceles to know those are congruent. Or I guess technically you could say LM is, well, we'll get to it. Okay. Anyways. And then we have, this is the midpoint, so we will be able to get this. And then we want to show that this angle, oh yeah, look at that. Okay, yeah. If we want to show that's perpendicular, well, let's just start at the beginning. We want to show congruent triangles. That's what we want to do in this whole chapter, right? But if we want to show these are perpendicular, what does it mean to be perpendicular? So let's go down and add the last step first, okay? So LN is perpendicular to, what was it, NP, MP. And so how do we get that two things are perpendicular? Again, that's a word. So we get that by the definition of perpendicular lines. And how do we get that things are perpendicular? Well, that's either, and I'm going to say right here, angle, all we need is one angle. So like angle MNL is right, or 90. So we don't know yet. I'm going to just throw that in there, something like that, right? So either of these two angles, if they're 90 or they're right angles, then by the definition of perpendicular lines, we could say they're perpendicular. So how are we going to get those are both 90? Okay, this is going to be a little longer. I think I might have to split this up onto a separate page here, okay? So let me pause this. I'm going to just move this other one down, so I think we'll need more space. Okay, I'm back. The reason I think we're going to need a little more space is just because I think we're going to have to delve into a little algebra here, and that'll just add a couple steps in the middle of the proof. So let's go ahead and figure out these two angles are the same. And then if they're the same and they sum to 180, they're going to be 90. So I think that's why we have to dive into algebra, and I created that space. So let's start. We know triangle MLP is isosceles, okay? And if it's isosceles, well then we know, oh, that was given. We know two sides are congruent. So then we know, and it has to tell us which in the picture. So we could say LM is congruent to LP. Now, if you wanted, you smart Alex, so I would say this is the definition of isosceles triangle. However, if you wanted, you could have said this was given by diagram, because they did literally write it in pink on the diagram. So you could validly say that. Now that's a little cheaty McCheaterson there, in my opinion. So let's use the given and go that way. All right, and then we need other things about these two triangles are the same. Well, what else do we have? We have that N is the midpoint of MP, okay? And we could use that. If it's the midpoint, oh, and that was given, then the definition of that says, well, if N's the midpoint, then from N to N is the same as the rest of the journey from N to P. That's the very definition of a midpoint. And so these are the same. And then we, of course, have this one in the middle is the same. So we have LN is congruent to LN by the reflexive property of congruence. Okay, well now if those three are the same, we have the triangles are congruent. So what are the triangles? Let's go in order. Let's go 1, 2, 3 for no reason other than, natural habit. So let's go, that's LMN is congruent to triangle 1, 2, 3, LPN, and that's by all three sides, so SSS, triangle congruence. All right, so now we're going to take this down a little bit, because we're going to need to do some magic here. So yes, using that, what that tells us is that these two angles must be the same, okay? So we know that angle MNL is congruent to angle PNL. That's by CP/CTC. That was the whole goal of finding the triangles are congruent. But now we need to off to the side say, well, we also know that angle measure of angle MNL plus measure of angle MNL PNL equals 180 degrees. I'm going to erase that and resize that box there. And how did we know that? Well, I'm going to go with the IXL version of linear pairs sum to 180. Now our book again uses the supplement theorem and then the definition of supplementary. I just like going straight to that. But we're not in equality over here. So let's get into the world of algebra with this other one. Let's take these angles are the same and say, well, that means the measure of the angles are the same, PNL. And so that's the definition of congruent angles. All right, so the angles are the same. And I could use this adds up to 180, and I could throw these two together. And we'll say, it doesn't matter which one I substitute out. I could go, well, that means the measure of angle MNL plus, and I'm going to substitute this one in. So I'm going to, again, have MNL equals 180 degrees. Right? And that was the substitution. And this is where just calling algebra gets in handy, because this would be like combine them to be 2 equals, then divide by 2. Instead, I'm just going to say that means the measure of angle MNL equals 90 degrees, and that was by algebra. So now it was 2 steps. I collapsed it to 1 and just said, I can solve an equation. We don't need to go through the solving. We are now fully into geometry. And if those are 90, that means that, oh, I lost a piece of my answer here. That means that the two lines are perpendicular by the very definition of perpendicular lines. If you really wanted to, you could say, well, that means angle MNL is right angle. You don't need to do this. And you could say that's by the definition of a right angle. You could just go straight to definition of perpendicular lines. Whew! All right, you guys, I hope you enjoyed it. I'm going to do this last little puzzle. Okay, in the figure, triangle ABC is isosceles and DCE is equilateral. And this other one's isosceles. Find the measures of these angles. So the key here is this is equilateral. So I'm going to go in and say, I know that angle, so DCE, I know this is 60 degrees. And I know this is 60 degrees. And I know this is 60 degrees. That's a key right there. Boom! And then it says ABC is isosceles. So the whole thing is isosceles. That means base angle. And I mean, it doesn't tell us which is which of, the 5 numbered angles at vertex. Well, vertex is kind of a loose of making the assumption. So we are having to make an assumption here of which sides of the triangle are congruent. So I'm going to go ahead and assume they're talking about like these sides are congruent when they say isosceles. We don't usually make that assumption. Okay, so what we have here is then that means this is 42 in the big triangle because of ABC is isosceles. And lastly, FCG is isosceles. So F to C to G. So that means this is 77. So then we can go ahead and solve for everything we want, right? We go in this middle triangle, 77, 77, yeesh. 180 minus the 277s is 140, 154. So that's 26 degrees. So here's 26 degrees. Okay. And then we have, this is 77. And so this is 103. And then we could, in this triangle here, say, well, 103 and 60 is 163. That leaves 17 degrees, I think. Let's try that one. Yeah. And then same thing here, 103, same thing here, 17 degrees. I mean, it's all isosceles and equilateral, so it's totally symmetrical here. And then we do the same thing here. So that means this is 120. So these add up to 162 in this triangle. And so that leaves over 18 degrees here. Let's check it again. So 120, that's 162, 162. Which is, I'm just double checking my math here. So that's 18 degrees. And then again, you could just always double check. Say, if I add all these up with 42 and 42, is that right? I'm going to check. So the two 42s add up to 84. We add all these up. Oh, I don't need to. This is, let's just double check, 34. So this is 60. So plus 60 plus 18 plus 18. That's 144 plus 36, that's 180. I just wanted to double check my work. Okay, not as challenging as I thought just from looking at it. Hope you guys enjoyed that video.